right, it's 9 o'clock. I'm getting started. Okay, so this time I'm double checking to make sure the recorder is on. And the screen is not set up correctly, so you guys cannot see anything yet. Give me a second here. Still nothing. All right. Oh. I knew I missed something. There we go. Okay, so I still need one more configuration to get it to work. It's interesting. Every time I hook it up, it reports in as a different device, which is kind of strange. There we go. All right. So the recorder is already on, has been recording for maybe a minute or two already. So what we'll do today is to focus on section 6. Remember on Tuesday, this is the last thing that we talked about, is how I wanted you guys to kind of read ahead of me, because this is kind of it's a difficult section in a way. If you're reading it by yourself, you might get lost in some of the details. All right, so we're going to get started here. So right now, because last time, we talked about a carry ripple adder. Do you guys still remember from Tuesday? Okay, I sent you guys the circuit diagram, or the logisim file, so you can actually look into that and understand exactly what a carry ripple adder is and how it is constructed. But the bottom line of that, or the disadvantage of that, has to do with ki plus 1 depends on k of I. So, for instance, the carry of bit 5 depends on the carry of bit 4. The carry of bit 4 depends on the carry of bit 3, and so on. And the bottom line is, if you have a 32-bit adder and it takes, let's say, 1 nanosecond to complete the calculation, a 64-bit adder would take twice as long. Okay, which is not a good thing, okay, because we want adders to be as fast as possible. So that's why we're looking into a different way to construct our multi-digit adder, so that we don't have that requirement. And that's the whole idea of what we call a carry look-ahead adder. Is that okay? Now, don't mind the name, because carry look-ahead, really is not a very good description of what it is. So what we'll do is we are going to focus on this really kind of messy equation first. And even though I will not require you guys to derive equations like this, I will still want you to understand it, okay? Because understanding this type of thing is just going to be useful in general, but it will not be in a test. I won't ask you to prove something like this in a test, okay? All right, so I can't really quite fit everything on the screen, because it's either this or this. So I'll start with that. Is the first row okay? Does everybody recognize the first row right here? I sure hope so, because we have gone through the definition of the carry bit a few times already. There are two sources to contribute a 1 to the carry bit of the next column. It can be the addition between the x and the y bits, but it can also be between the cube, which I call a partial sum, and the carry of the column. So both of those can contribute. And remember, this plus here is not an arithmetic addition. We already talked about this on Tuesday, of how we can use a logical OR in place of an arithmetic addition, because it is not possible for both sides to be true at the same time. Is that okay? All right? All right. So from the first row to the second row, Do we have any questions about that? How did we go from the first row to the second row? What allows us to go from the first to the second row?
That's what the carry function is find out.
Exactly. So in base 2, okay, it doesn't work in other bases, but in base 2, the carry function is really just a conjunction. So that's how we can go from the first row to the second row. Okay, what about from the second row to the third row? That should not be too difficult either. So from the second row to the third row, the only change is qi becomes r of xi yi. And that is because that's how q is defined. Q of I is just defined to be r of xi yi. Okay? So far, we are just going by mostly just by definition and also by the structure of a multi-digit adder. So no big thing up to this point. From here to here, from the third row to the fourth row, how did I make that transformation?
Base 2 definition.
Sorry?
Base 2 definition for QI.
The base 2 definition of the R function, or QI. Yes, that is correct. So this is just exclusive OR. But since, in the question I said, let's do this without using any logical operators that we have not used in C and C++. So I confined to the use of conjunction, negation, and disjunction. Is that okay? All right. From here to here, I have to explain a little bit, okay? So the first 4 rows should not really have any questions at all. Okay, if you are thinking about, okay, I don't quite understand how we went from one row to the other within the first 4 rows, you really need to kind of review the material and make sure that you understand the material, because the first 4 rows is really just coming from the stuff that we have talked about. From the 4th row to the 5th row, between these two, now I have to start explaining, because this is the distributive law in Boolean algebra. It's the same thing as what you use in normal algebra. Okay, 1 plus b in parentheses times c is ac plus bc. Okay, as it turns out, that rule works in Boolean algebra as well. So that's how we went from the 4th to the 5th. From the 5th to the 6th is also new because it is also Boolean algebra, but it is not unlike 1 being the identity of multiplication in normal algebra. Okay, I hope you guys remember, if you multiply anything by 1 in normal algebra, you just get the original thing back. Okay, multiplication by 1 doesn't do a single thing. And as it turns out, in Boolean algebra, and 1 or and true doesn't do anything. Now, how do we know that? How can we convince ourselves that x and true are really the same thing? A truth table, very good. So when x is true, what is true and true? True. When x is false, what is false and true? False. So you can see how the 2 columns are exactly the same, and that's why we can establish that true is the identity of conjunction in Boolean algebra. Is that okay? So it doesn't seem very smart to introduce something like this, right? I mean, we had a simpler equation to begin with, or an expression. Now it is a little bit more complicated. Now this is what, row 6 to row 7, that is a little bit of a stretch, okay? Because if this appears to be awkward, okay, or not true in normal algebra, but in Boolean algebra, it works. In other words, if I say true here, I can say true or something else. They're really the same thing. Because what is true or false? It's still true. What is true or true? True. So it doesn't even matter what ki is. True or ki is really just true. Is that okay? So this is where Boolean algebra is a little bit different compared to normal algebra. Yes?
Can you explain why we do that in the first place?
Why we do?
Why we're doing 1 or ki like in the first place for this?
Because then I can use it in a distributive law application. Yep. So I'm setting up for further steps. Yep. Yep.
Is it a law? Like it's just
It's more or less an axiom or a law, but it is provable by using a truth table. So anything that you can prove by a truth table in Boolean algebra, you can consider that as a law, as an axiom, because you don't need further explanation of why that is the case. The truth table is sufficient to prove that it really holds. So that's kind of cool because you cannot do something like that with normal algebra. Okay, because with the normal algebra, which applies to numbers or at least integers, there's an infinite number of integers. So there's no way you can actually look up a table and say it works for all cases. But in Boolean algebra, there are only 2 values per variable. So we can actually use a truth table to establish axioms. Are we good? Okay. How about from here to here? I lost track of which row we are talking about. From here to here is just what? Distribution. Okay. So it doesn't seem to make sense, right? I started off something that's way simpler and now I have something that's more complicated, right? And it gets even worse. From here to here, what did I do from here to here? I added an extra term, didn't I?
Yes.
Which extra term did I add? This is just that, right? This one is added. So I take this one here and I say, I'll make another one here. Is that okay in Boolean algebra? It's okay in Boolean algebra, not okay in normal algebra, but in Boolean algebra it is perfectly okay. Because the question you need to answer is, what is the relationship between x as a Boolean variable and x or x? What do you think? When x is true, what is x or x? It's also true. When x is false, what is x or x? It's also false. So that means x and x versus, I shouldn't use the word and because that adds to confusion. So if you look at x versus x or x, they are actually the same. So that's why I can take this guy and say, oh, I would just add one more term here related to this one using or. Now, of course, from here to here, I also used the commutative law in Boolean algebra a few times just to move it along to the other side, to line up things. But nonetheless, the ultimate trick to go from here to here is just to repeat a term in a disjunction. Is that okay? So the mechanism itself is very simple, okay? But why do I do that? Well, I'm setting it up to do this. So I'm now regrouping everything so that I can add extra parentheses around these two, and I can add extra parentheses around these two. That's associative, okay? If you want to know which law we are applying, that's associative, which means if you have a whole bunch of stuff in a disjunction, how the ordering of which one is ORed with which one first does not matter. It's just like with addition in normal algebra. It doesn't really matter how you reorder the addition or how you throw in additional parentheses. As long as you're still dealing with the same addition of the same terms, it comes up the same. So that's why I can put extra parentheses. So after I put in the extra parentheses, then I use factoring, which is also a trick that you normally can do in normal algebra. So I look at these two terms and go like, hey, they both have xi and they both have ki. I extract that, I factor that out. So what is left is just yi from here and then not yi from the other one. Is that okay? It is also a technique borrowed from normal algebra. It also works in Boolean algebra. Look at this as the reverse of distributive, right? It's really the same thing, except it works in the opposite direction. Same thing over here. I look at these two terms and go like, well, they're slightly different because one has xi, the other one has not xi, but they both have yi, ki. Okay, so I factor out yi, ki, and then I take whatever is different and make a disjunction out of that on its own. So same trick, it's just factoring. Are we good so far? Okay. So from here to here, I use a simplification. Now this one does not work in normal algebra. Y or not y is always true. Now, can we prove that one? Truth table will do it, right? When x is true, then we have true or false, which is true. What if yi is false? Then we have false or true, which is also true. In other words, regardless of the value of yi or not yi is guaranteed to be true. So I can simplify this to true, and using the same reason to simplify the other one also to true. Is that okay? So from here to here, I just get rid of the 1, or get rid of the and true, because if I can introduce and true here, I can get rid of it as well. Because it's the same thing as blah, blah, blah multiplied by 1 in normal algebra. Okay, we don't need that, right? So I just remove the and true from that expression. So once I remove the and true, I just get these 3 left, and then I do factoring one last time so that I extract ki out of the last 2 terms. So ki is now on its own because it's factored out, and then we have just xi or yi left inside this conjunction. Disjunction. So are we good so far? So once again, this is not cisp310. This class is not about proofs, so I'm not going to ask you guys to to prove something with this many steps. But on the other hand, I want to give you the exposure. I could have just easily said, oh, that expression up there is the same thing as this expression down here. Done. But I cannot do it that way, because if I want to teach something, I have to first convince myself that that works. And this is how I convince myself that it works. Is that okay? So it's an exposure, okay? In this class, something like this is really just an exposure of Boolean algebra. You're not required to know how to derive equations in this class in Boolean algebra. But it will be useful in cisp310. If you have not taken 440 yet, this will be helpful. If you want to become a computer engineer or an electrical engineer, you will see these again. Okay, you'll be working with Boolean expressions using Boolean algebra all the time if you become a computer or an electrical engineer. Now, in computer science, it's kind of questionable, how much Boolean algebra you will actually need to know, but the more you know, the better. Because regardless of whether you become a programmer, a developer, a software engineer, a computer engineer, or electrical engineer, knowing how one expression is equivalent to another expression is always helpful. Why is that the case? What if somebody says, but I really just want to develop games, okay? Why would this help me in the development of games? What do you think? Yep.
Well, if you want the game to be more diverse and have different sort of logics, like say decisions or branching paths, you have to follow logic. You would have to follow different patterns.
Boolean expressions, right? You have conditions, right? So regardless of what type of programming you're doing, you can be doing web scripting, you can be developing a game using one of the game engines, you can be working with really old programs in COBOL, okay? But regardless, conditions and conditional statements and loops are always going to be there. Question? Yeah, go ahead.
Games also have to worry about parallel processing. It's one of the ways in which they can speed up.
Yep.
They have to be fast and do
Yep.
a lot of collisions.
Okay. So in that case, the idea of a carry look ahead mechanism is useful because we are trying to speed up the process of addition. But when it comes to knowing that this expression is doing exactly the same thing as the original expression, it's because when you become a developer, you might need to read the code of somebody else. Okay? Someone else may choose to express this logic using the original form. You have to know, you should know, that that form of an expression is equivalent to this form of this is an equivalent expression. So that is useful because when you write a program or when you become a developer, you are not the only person writing code. Most of the time, you'll be reading somebody else's code, or your code has to be modified or debugged by somebody else. So knowing how one expression is equivalent to another expression is actually a useful skill to have. Okay. It's something that you do not have any experience up to this point, because up to this point you have your homework assignments, right? Your projects, and they are supposed to be individual. So you don't have the experience of having to maintain a code base that has like a million lines of code, contributed by like hundreds of developers over like 30 years. I'm talking about the Linux kernel, by the way. Okay, so if you need to work with the Linux kernel, understanding Boolean algebra can be a great help. Okay, all right. So moving on. So to move on, I am going to define two additional terms. One is g of I. So g of I is just defined to be xi and yi. That's all. That's how it's defined. And then we have p of I, which is defined to be xi or yi. They're just defined that way. Okay. So at this point, we are not questioning why they are defined that way. We're simply saying every time you see xi and yi, you can use g of I instead. Every time you see xi or yi, you can use p of I instead. You can look at this as a shorthand. Yeah, I think it has to do with the cable, or yeah, something is not. Yeah, streaming part is still going. I know that part is still okay. But I think the screen resolution is changed because of that. Let me double check. Yeah. Yeah, these projectors are actually capable of wireless connection. They just have not enabled it. It would be nice if I don't have to hook up the cable and stuff. So anyway, so are there any questions about the definition of g of I and p of I? They're simply defined that way. Okay. Now, when we look back into this, the final form of this expression, do you recognize g of I in here? Yeah. Well, we can take this xi and yi and turn it into g of I. Do we see p of I in here? Yeah. That's p of I. So it doesn't take a whole lot of effort to understand, oh, okay, so we can redefine k of I plus 1 to be g of I or p of I and k of I. Is that okay? So from here to here, it is just a notation change. Okay, the meaning has not changed. There's no derivation. All it is just notation. But at this point, we still have not removed the linear dependency of ki plus 1 on k of I. I mean, it's pretty clear. K of I plus 1 relies on k of I. Okay? So it would appear that all this work is just going to waste. Why are we doing this? It's not helpful in any way. So what we'll do is we'll now apply this general equation to cases of what happens when I equals to 0, what happens when I equals to 1, what happens when I equals to 2, and so on. Okay? And we'll start with the easy one, when I equals to 0. When I equals to 0 over here, 0 plus 1 is 1, and we'll be referring to g of 0, p of 0, and then k of 0. And we end up with this expression here, or this equation here. Do we have any questions of how we got to this equation, which is k of 1 equals to g of 0, or p of 0 and k of 0? Should not have any problem because it's just a direct application of the general equation. Is that okay? So when I ask you, does k1 depend on k0? The answer is yes, most definitely. Okay. Then we move on to k of 2. So when you look at k of 2, we plug it into this general equation when I equals to 1, right? So when I equals to 1, then we have k of 2 equals to g of 1 or p of 1 and k of 1, which is what we have here. Then you will say, but that doesn't get rid of the dependency. K of 2 is still depending on k of 1. But you know what? We know what k of 1 looks like now, don't we? This is what k of 1 looks like. So what if we take the definition of k of 1 using this equation and plug it into here? So now we have that. Is that okay? Does everybody understand this portion of the equation, of the derivation? This k of 1 becomes this because we derived k of 1 earlier already. Is that okay? And then what we do is we apply distribution again, and it becomes g of 1 or p of 1 and g of 0, or p of 1 and p of 0 and k of 0. Do you see any significance of this derivation? Where's k of 1? It's gone. Okay? By using this substitution here, k of 2 does not depend on k of 1 anymore. It only depends on k of 0, which is one of the input pins, just like x and y. That is cool, because it seems like we have broken the linear dependency of the carry bits. Okay? Let's just say that we are not totally convinced. So we look at K3. So if we look at K3, we can once again plug it into this general equation first. And we say, what if I equals to 2? When I equals to 2, then k of I plus 1 is k of 3. It is defined to be g of 2 or p of 2 and k of 2. So we'll start with that. So we start with that. But by this time, we also know what k2 should look like because of the earlier derivation. So we take this equation and say, hey, k of 2 is really just this. So instead of using k of 2 here, we just put in the longer form that expresses k of 2. Is that okay? So by the second row of the derivation, we have already removed the dependency on k1. But we go one step further. We apply distribution again. So now it looks like this. So do we have any questions about the derivations themselves? Okay. Are there any questions about how we got rid of the linear dependency? Everybody just depends on x, y, and k0 now. Is that okay? But then somebody would look at k3 versus k2 and say, but k3 is still significantly more complex. It's going to take more time to evaluate k3 compared to k2, so we are not winning. We're still losing because k3 is going to take longer to evaluate. Is that true? Is that statement valid? Just because we look at it, it looks more complex, does it mean that it's going to take longer inside the computer to evaluate? That is the question. What do you think? I claim that they will take exactly the same amount of time. And you go like, whoa, why? This is definitely longer. Okay. So the first stage of the calculation is really to compute the g and the p terms. Okay? But can they all be done in parallel? Can I compute g0, g1, g2, p0, p1, and p2 all at the same time? Okay, let's think about what each term depends on. G of I depends on what? Xi and xi, yi. P of I, kind of the same thing. One goes through an AND gate, the other one goes through an OR gate. But nonetheless, they're all just depending on the original input pins, the X and the Y pins, right? So nothing is going to stop me from computing and getting G0, G1, G2, P0, P1, P2 all at the same time. Does it make sense? So that means I have to spend a little bit of time to get these individual terms computed. K0 is an input, doesn't need to be calculated. So once I have all the P and the G terms, what do? The second level of gates will be doing the conjunctions. So I take P2, G2, make a conjunction to compute this. I take G0, P1, P2, use a larger AND gate with 3 inputs to compute this term. And then I take K0, P0, P1, P2, and have an even bigger AND gate to compute the conjunction of these 4 terms. But a conjunction gate or an AND gate with 4 inputs is in theory as fast as an AND gate with only 3 inputs or 2 inputs. So that means the result of this, well, this one is a little bit extra because it doesn't have an AND gate, but I can get to the result of these at the same time. This is already done by the time the other 2 are done. So now I just need to take the result of this, the result of this, and the result of that, and feed them into an OR gate, and I have the final answer. Is that okay? Same thing over here, except the final OR gate now has 4 inputs. 1, 2, 3, 4. But all 4 inputs are available at pretty much the same time except for the first one. So now I just have to go through the OR gate to finish the entire calculation. Is that okay? Are we kind of visualizing the whole thing? Yep.
I don't know if we have enough time, but can you actually make an example of the AND gates?
Sure. I can draw it out instead of using Logisim because I think I can draw this a little bit faster. So it means it's not going to run in Logisim, but it will give you an idea of what I'm talking about. And it's probably a good time to double check my recorder is still on. Yep, it's still on. The voice is still there. Okay. So let's make a new page after this. Okay. So this is going to take me a little bit more time. Okay, so in that particular example, we have x0, y0, and if I feed these 2 into a AND gate, that will give me G0. If I feed these 2 into an OR gate, that will give me P0. Is that right? Okay. So I'm not going to replicate this for G1, P1, G2, P2 because it's kind of the same thing, right? It's just that G1 would depend on x1, y1, and then G2 would depend on x2, y2, and so on. Is that okay? So is it okay for me not to show the exact gates, but just to show that I can get to G1, P1, G2, P2 with some one level of gate from the inputs. So the idea is there's only one gate or one propagational delay between the XYs and the P and the Gs. Is that okay? Well, I have a question. Why is there a delay? Why is it not simultaneous? In other words, when I change x0, why is g0 not changed like instantaneously, like there's no time delay in between? I mean, I really should answer that question first. Why is there a propagational delay? Yeah, go ahead.
Resistance?
There's not just resistance. Resistance is a part of the explanation. So I'm going to draw this simplified diagram. I'm not going to make the entire thing this time, but I think you guys recognize what it is, right? Okay, so you guys recognize this thing, and I'm not going to show how the gates are connected or the P versus the N. I'm just going to show you a very rough draft of something that we already know, which is the NAND gate, right? But what I want to focus on is how does a transistor work, right? So this is called a field effect transistor. If I were to take this and kind of take a closer look, this is kind of what it looks like in terms of the schematic. But it is actually representative of how it is made physically. If you see something like this in an electrical circuit, what does it resemble? A capacitor. Very good. So yes, so it is actually true that every field effect transistor has a built-in capacitor to it. So what that means, for those of you who have not taken electricity or electronic circuit design, is in order to change the state, you have to charge it up. Okay? In order to change the state to the opposite, in the opposite direction, you have to discharge it. So you have to have, basically you need electrons to move into this direction and start to accumulate on this plate. And also you need electrons to get out so that you don't have extra electrons on that plate. So on top of everything else, every time you have a conductor like wires, there are always resistance involved. Okay? There's always a built-in resistor somewhere along the line because nothing is a perfect conductor. We wish we have perfect conductors, but we don't. Okay? Why do we want perfect conductors? Think about a world with perfect conductors. Okay? Yep.
There's no resistance, so everything will happen instantaneously.
It will be more instantaneous, but as long as you still have inductance and capacitance, it won't be exactly instantaneous, but it won't get heated up anymore. Okay, so your Tesla, will be super efficient because all the electrical energy is actually used to propel the car. None of that is heating up anything. Okay, anything that has a motor in it is not going to get hot because the wiring has no resistance. The resistance is things to get hot. Okay, now if you think about it from the perspective of a processor, if we can have conductors that do not have any resistance at all, you won't need a heat sink anymore. Then you can make even smaller devices because you can pack things into a smaller space with no heat sink, no heat pipe, no fans, nothing, and it will still work. And it will work even faster. Unfortunately, that's fantasy. Sorry? Yes, it is fantasy right now, and part of it has to do with we're living on Earth, and we ourselves require somewhere between 68 Fahrenheit to about 80 degrees Fahrenheit to function normally. Okay, because we do have superconductors that can operate at liquid nitrogen temperatures, but we cannot. So anyway, what does that have anything to do with this? Every time you want to turn on a transistor, every time you want to turn off a transistor, every time you want to change something, it takes time. Okay? So that means from the moment you change the x0 and the y0 to the moment that g0 and p0 reflect the correct results, there is a propagational delay. There's a certain amount of time in between the transitions of the input to the transitions of the output. Is that okay? So I'm just explaining why there is a delay. Okay. Now that we have all the P's and the G's, then what do we do? Well, it kind of depends on which term we are looking at. So I'm just going to go back to my notes here. Let's just work with K3, okay? So G2 is on its own. So we pick out G2 and we say, okay, you are fine, okay, you're done. And then we look at P2, G1, so those two need to be ANDed. So P2 and G1 need to be ANDed. So these two, P2 and G1, they need to go through an AND gate. And then we have G0, P1, P2. So we have G0, P1, and P2. They have to go through another AND gate. And then the last one is even messier. It's got K0 and then all the P's. So let's say K0 is here. So now we have K0, P2, P1, and P0 all going through the same AND gate, right? So when you look at these three AND gates, can they get started at the same time? They can get started at exactly the same time because all the P's and all the G's, well, assuming AND gates and OR gates operate at the same speed, all the P's and all the G's become available at exactly the same moment, right? And all of these only rely on P and G gates, P, G, and K0. So that means they will all come up with the right answer all at the same time. So this guy comes up with the right answer at the same time, and I think one of them, G2 is on its own. Okay, so G2 doesn't need any delay, or it has a minimal delay because it still needs to go through one single AND gate. This will come up with an answer, this will come up with an answer, but these four will be available at the same time. So now I just need a big, huge OR gate on top of everything like that to come up with the final answer, which is K3. Is that okay? So when you look at it from this perspective, then it will take 3 gates of propagational delay to come up with the carry. The first propagational delay is just to get to the P and the G terms. The second propagational delay are for the individual AND operations. And then the last propagational delay is for the OR, that is the umbrella that covers everything. Is that okay? So now the question is, well, if K3 looks like this, what about K2? K2 will be simpler, okay? But the question is, how many levels of gates do we need? It will still be 3 levels of gates. What about K64, which is going to look really ugly, right? Because it has got 64 terms, and then one of those terms has 64 individual terms within a conjunction. But how many levels of gates are we talking about? 3. So if we assume, regardless of the number of input pins, a gate has the same propagational delay, then all the K's can be computed at the same time. And they will all finish at the same time as well. Now, how does that compare to a carry ripple design? A carry ripple design cannot do this, right? Carry ripple design says K64 depends on K63. K63 depends on K62. K62 depends on K61. And you just have a long chain of carry bits. So the propagational delay to get to K64 in the case of a carry ripple design is really long because it's 64 times how long it takes for carry in to affect the carry out of a full adder. Remember the concept of a full adder from Tuesday? So that's really long. This is way faster. So are we understanding the mechanism that makes a carry look ahead design like this much faster compared to a carry ripple design, which is what we talked about on Tuesday? Okay? All right, so this is good. So we look at this and go like, I think we have a general method of generating, K of something. Because we look at, we generate K3 out of K2, K2 from K1. So in theory, we know how to get to, let's say, K64 with a 64-bit adder. But do you want to do that? I mean, I don't even want to work with K5, okay? K4 is pushing my limit. K5 is like, why am I doing this? It's kind of like, making me do dishes when there's a dishwasher next to me. So now we want to look at the general equation. It's like, if I want to compute Ki plus 1, what does it look like? Well, that's what the last expression here is for. Okay, this is the generalized carry bit generator, so to speak. So you have not seen these symbols prior to this class. I don't think so, okay? This is the OR operator. If you ignore everything else and just look at the symbol itself, that's the OR operator. If you ignore everything else, this is the AND operator. It's basically a summation thing. It's the same thing as a sigma, which means each one is specifying a loop. Okay? So it's specifying a loop. It specifies the index that you use to go through the loop. We go from 0 to n in this case. And because I is already determined by the time we get to this part here, so this j goes from I plus 1 to n. Okay? But what are we doing with each iteration? Well, it depends on where we are. With the v, for each iteration of the v, we're trying to compute this term. With this one, we're trying to compute just that term. Is that okay? So it looks awfully ugly. Okay, you can turn it into loops. Okay, that's the bottom line. But I want to show you how we can come up with just K3 using this generator. Because if I go through that exercise once, I think you will understand the mechanism of how this works and how to generate the other K terms. So that's what we'll do next. And to do that, I am going to use just a mouse pad here. This is from the previous class, so it was done already once yesterday, but I'm going to do it again. All right, so the way I express this is n equals to 2. So when n equals to 2, we are trying to compute k of 3, because n plus 1 is 3. Is that okay? So once I have fixed n, I can at least look at the other side and just re-express that. So I will say k of 3 is, I'm going to use all uppercase OR to represent the big V notation. And I'm just going to use the C notation of I equals to 0 to n to indicate that I is the indexing variable, and then the range is going from 0 to n. Is that okay? So it's just a translation from something that looks really nice on paper to something that I can easily type in a text editor. Okay? All right. So once we specify the iteration, the loop itself, now we have to specify what is the term that we need to evaluate. So we got g of I, and this is ANDed. It's ANDed with whatever is next, because between the g of I and this thing here, there's a hidden multiplication here. And multiplication means conjunction in a Boolean expression. Okay? So, but I'm spelling this out, entirely in say and. And then what is inside the parentheses here is a big AND, because it's a loop by itself, where the indexing variable is called j. The start value is I plus 1, and the end value is n. And with this big AND here, the term that we're ANDing is just pj, so that's a relatively simple thing to do. Huh? Say that one more time?
Screen is not showing.
Oh, okay. Let me move things around a little bit so it shows. There we go. Okay, much better. So now I need to match the parentheses. I think I just need to close it one more time, like that. And then we have an OR. So this bar OR is this OR up here. Okay. So on the other side of this OR, we have K0 and then we have a big AND, because it's a loop, big wedge. And then we have I equals to 0 to n. And then each term is just pi in this case. So are we doing okay so far with this transition? I'm just translating something that looks nice on paper to something that I can actually type using a text editor. Okay? But we already know what n is. So let's go ahead and substitute all the n's with a concrete value, just so that we make it easier to read that way. So we just look at all the n's and go like, okay, n is just 2. N is just 2, and n is just 2. Is that okay? Because we are working out a very specific case when n equals to 2. All right? So the next one will look kind of confusing, because what I'm doing here, okay, there's an equal here. So the next one is going to, is for me to unfold the for loop corresponding to this big OR. In other words, what I'm doing is I'm going to spell out this term over here for each possible value of I. Okay? So can someone just tell me what are the values of I according to the big OR notation here? I'll highlight which portion. So what values do you think I would assume for the 3 iterations? I would be 0, I would be 1, and then I would be 2. Okay, very good. So all I'm doing here is unfolding it. When I equals to 0, do the following, and then OR. When I equals to 1, do something. I'll finish it later, but I want to give you the overall layout first. Okay? So the rest is kind of the same thing as last time. We'll keep this part the way it is. So we'll just expand one thing at a time. So I'll keep that one over here. So what would the rest look like? The same as before. I just take the term that I'm supposed to be evaluating for each loop and stick it here. I'll expand and deal with the I later on. Is that okay? So all I'm doing is to say, well, instead of looking at this big OR notation, let's spell out what happens for each iteration and what we're doing about the term for each iteration. It just relates to the next term of the term of the next iteration through a logical OR. Is that okay? Yes? Okay? So if that is okay, I'm working on this really step by step, so this way we can see how we make all the individual transitions. Now for this line here, I is a constant, isn't it? I is already fixed to a value of 0. So everywhere I see I just replace it with 0. Is that okay? I mean, I can just change this to 1 to n. And I don't need I anymore because I is just a constant. I have already substituted all the i's with a constant. Is that okay? Okay, I'm going to do the same thing with the second row. G of 1, and this is 1 plus 1, which is 2. Oh, I forgot to substitute all the n's too. N's are 2's. Okay, there we go. Okay. And since I don't have any references to I anymore, I can get rid of that. Okay? On the third row, same deal. This is G of 2. This is 2 plus 1, which is a 3. And since I have no references to I anymore, I don't need that. Are we good so far? All right. So we take this. Let me check the time. So we take this, copy, paste. And this time I'll just deal with this loop here. This is the inner loop of the end. Okay. So once again, how many iterations do I have to go through with this big end notation? It's not 3 iterations anymore because J starts with 1. So we only have 2 iterations, isn't it? Right? J equals to 1 is 1 iteration. J equals to 2 is the other iteration. Is that okay? How do we relate the terms of each iteration in this case with the highlighted portion? They're all ANDed together because it's all inside the big AND notation. Okay? So we'll change this notation and we'll just say J equals to 1, and the term that we're interested in is Pj, and J equals to 2, and the term we're interested in is also Pj. Okay? And what about this one? What would that become? How many iterations do we have? 1 iteration, and J has a value of 2. Okay, very good. So we just say this boils down to J equals to 2 and Pj. Okay. What about this one? This doesn't seem to make a whole lot of sense because the start index value is larger than the end index value. So if you specify a loop like this, you're not going to go through any iterations. So it doesn't produce any terms at all. If it does not produce any terms, we just get rid of it, along with the conjunction that is that connects it with the rest. Did I do the right thing? Okay, I think I messed up the notation somewhere. Okay, so we just get rid of this entire thing, but we leave the G2 over here. There we go. Are we still doing okay so far with this? We still have one big and down here. Let's finish that one too. So this one has how many iterations? It's got 3 iterations. I equals to 0, I equals 1, I equals 2. Okay, let's spell it out. I equals 0, and what we are interested in is pi. And how do we connect it to the next term? It's ANDed with the next term because it is corresponding to a big AND notation. So it's ANDed with the next term, which is I equals to 1, pi, and the last term is I equals to 2, pi. Okay? So we take this and go like, it looks kind of messy. Can we simplify this a little bit? And the answer is, oh yeah, we can definitely simplify that. Because if you look at this, what is that really saying? P1. All right. And that makes this one pretty easy too, doesn't it? That's just P2. Okay. And because this is a conjunction, so we can remove the extra parentheses because they're associative. What about this guy here? That's just P2. All right. And down here, I think we are convinced this is just P0, P1, P2, right? And we can get rid of the parentheses. Actually, we should add 1 out here. Even though in terms of the convention, conjunction has a higher priority compared to disjunction, it doesn't hurt to add the extra parentheses to emphasize. Okay, does that look familiar to you? It should, okay? Because what this is specifying, let me just kind of move this out of the way for a short time. And take that over there. And see if we can see both at the same time. I think we can. There we go. Do you see how we got K3 back? I mean, things are ordered a little bit differently, but if you understand that, you can change. If you understand that conjunction and disjunction are commutative, then you can see that those two expressions, this one versus this one, is really the same thing. So that is how you apply that kind of awkward looking expression to generate the carry bit of whatever. Just specify your n. It has to be at least 0, okay? But then you can generate any term you want. The idea is you can turn this into code. You can write a C program, C++ program, a Verilog program, a VHDL program, and use this to generate the logic of whatever carry that you need to generate. Is that okay? So do we have any questions up to this point regarding the carry look-ahead mechanism?
Would you ask this on an exam with different values?
Well, it's very tedious, so I tend not to ask tedious questions or questions that have tedious answers, which is not really answering your question, but it is telling you what my preferences are. Any other questions? Do we understand the whole derivation of carry look ahead? Cool. All right. So your lab today is kind of a part 1 of a 2-parted lab. So part 1 of the lab is to build a relatively simple circuit, which eventually will become a 3x3 carry look ahead adder. Okay. So you probably don't want to reuse any component from your 3x3 carry ripple adder because it really does not apply. Okay, so we'll during lab time today we'll work on a circuitry that relates to carry look ahead. Okay, so without any questions of carry look ahead, we are going to move on to subtraction in base 2. Is that okay? Do we have any questions lingering regarding binary addition? No? Yep.
So, when we were on the whole formulas and the execution of the formula.
Oh, you mean the big long derivation thing?
Yeah.
Okay, so let me move back there so you can refer to it. This part.
So with the 1, we know it was always true. If we know it's always false, can we just say it's 0?
Yes. So so false, which is 0, is the identity of disjunction. Anything or false is just that thing itself, which is equivalent to, in normal algebra, anything plus 0 is the original value. But in this particular proof, it was not needed to introduce a false. And it did its thing again. I have to find out exactly what is causing this because it's just disrupting. It's disruptive. I can. No, I cannot do it now. I have another HDMI to VGA converter, but that thing is a little bit bigger. And because I also have this USB dongle, I don't have enough space when they're right next to each other. And I don't want to unplug the dongle because then we'll lose the audio for recording. Okay, so there's that. So let's work with binary subtraction. So I hope you remember when we talked about binary addition, there were 4 cases. And there are also only just 4 cases when we talk about binary subtraction. So just like with binary addition, before we talk about binary stuff, let's talk about base 10 stuff first. What is 3 minus 7? -4. 3 minus 7 can be seen as -4, but it can also be seen as a 6 with a borrow. Okay? Okay, so let's focus on this first, okay? The concept of a borrow is analogous to the concept of a carry, except one is applicable when you're adding, and the other one is applicable when you're subtracting. Okay, so the analogy, the easiest way to visualize this is you think of me and I have, what did I use again? 3, right? So I have $3 in my pocket, okay, right now. So that's the 3, the number to be subtracted, okay? There's a bully standing right outside of the classroom, and the bully is going to demand $6 out of me. Is that okay? So it is equivalent to 3 minus 6. But I only got $3 in my pocket, and I don't want to be beaten up. So what am I going to do before I walk out of the classroom? I go like, hey, you got a 10? Right? So you will lend me a 10, okay? And at some point, I'll remember to pay you back. But how much do I have now? I have the $3 that I had, right? Plus the $10 that I borrowed. So how much do I have at least for that moment? I have $13, okay? I get outside of the door, I get out of the door, and then I give the bully the $6. How much money do I have left in my pocket? $7, okay? But I actually do not own the $7 because I have an IOU. I owe you $10. So my net worth is still 7 minus 10. I'm still having a net worth of negative what? $3 in this case. But it is expressed as $7 in my pocket but I owe you 10. Is that okay? That is the concept of borrow. Are we doing okay so far with that concept? So now let's switch to binary numbers, okay? Which means that we're only dealing with $1, $2, $4, $8, okay? I got $1 in my pocket. The bully says he wants 2. I should not be gender specific, but since I already said that, he wanted $2, okay? No, I take it back. Okay, never mind. Take it back. I have nothing in my pocket. Okay, I did not bring any cash with me today. I got $0 in my pocket. Okay, the bully outside says wants $1. Okay, I don't want to be beaten up. I'm gonna ask you to borrow money. What do you think I'm gonna borrow from you? What is the quantity I'm gonna borrow from you? $2. Very good. So I borrowed $2 from you, so I would have $2 in my pocket when I walk out of the door. I give 1 to the bully, and how much do I have left in my pocket? I have $1 left in my pocket, but I still owe you 2. So I have a borrow, even though I have $1 in my pocket. Is that okay? Now, why is it the case when I borrow, it is always one denomination higher than the denomination that I have? Because that guarantees that I will have enough money.
Yes.
Yep. So is that okay? All right. So with that in mind, we can now go look at all the scenarios in base 2 subtraction. We'll work with the easy one first. Okay. 0 in base 2 minus 0 in base 2 is what? 0 in base 2. And do we have a borrow? With a borrow of 0. Okay. What about 1 minus 0 in base 2? 1, okay, with a borrow of 0. Okay, that doesn't seem too hard. 1 in base 2 minus 1 in base 2 is 0 in base 2 with a borrow of 0. Okay. So the only case that's kind of tricky is what I said earlier. I got no money in my pocket. The bully wants 1. So now I need to borrow $2 because the next denomination is 2. With $1 left in my pocket, but I have to remember that I owe somebody a $2 bill. So with a borrow of 1. Now, I realized that I said I borrowed 2. But I have a borrow of 1 unit of the next denomination. So this one is not saying it's a quantity. It's not $1. 1 bill of the next denomination.
So it's like 10 in base 2.
In base 2, it will be a 2. The quantity will be 2. In base 10, the quantity will be 10. Is that okay? So are we doing okay so far with this concept? Okay. So now what we want to do is just like what we did earlier. We look at x and y. So this time x and y we have to be very clear about which one is x and which one is y, because subtraction is not commutative. You cannot switch the order. Okay, this is going to be our result. I would still call this the result, and this is our borrow. Okay. So let's look at the result first. So this is the simplified table to only focus on the result. 0, 0 has a result of 0. 1, 0 has a result of 1. 0, 1, which is the tricky case, also has a result of 1. And then 1, 1 has a result of 0. Does that look familiar to you? It should. This is the reason why I kept using the letter R to refer to the result. Because it doesn't matter whether you're adding or subtracting, the result of the operation remains exactly the same. So what is the difference? How is subtraction any different from addition? It has to do with the borrow. So this time we focus on the borrow bit. 0 minus 0 has a borrow of 0. 0 minus 1 has a borrow of 1. 1 minus 0 has a borrow of 0. 1 minus 1 also has a borrow of 0. That doesn't look like carry to me. Because if it were carry, then this one would have been at the bottom, and that would have been a 0, right? Okay. Then what do we do? How do we? This one we know what to do already. So the result of xy is the same as before. It is just exclusive or if you want to spell it out the long way, it is the same as before. You don't have to write this down. It's just, not xy or x not y. Okay, just like before. But this time, the borrow bit is a little bit different. How do you think I should express that? Well, anytime, if there's only one row that has a 1, it's actually pretty easy. Because you can basically just say, oh, I need this row to have a 1. So I can look at this and say, how can I turn this into a 1? Negation. So I negate the x and y. That becomes the expression. Huh? Exactly. So good thinking there. Very good. Good job. So instead of just x and y, it becomes the negation of x and y. Now you can double check and make sure that it works out for all of the other rows. The other rows would come out as a 0. Pretty sure that is the case. Is that okay? This is great. What about multi-digit subtraction then? Okay, so with multi-digit subtraction, once again we have x2, x1, x0, but this time it is a subtraction, y2, y1, y0. Okay. And we have the same thing here. We have q2, q1, and q0. And over here, I'm not going to use k because they are actually different. I'm going to use t. t2, t1, and t0. And over here, instead of using sum, it's d for this difference. So we have d2, d1, and then d0. Okay. So what we want to do is to say, well, how do we get to the q terms? What do you think? The same way as before. Okay. So q of I, okay, and I can use bracket to indicate the index. So q of I is the same thing as before. It is the result of x of I and minus y of I. Is that okay? What about t of I? So now to answer that question, let me give you a base 10 subtraction first. Then you guys will be able to answer that question. So let me think of a case where we have borrows. Okay, so we have 9, 1, 0 as base 10 minus 1, 1, 9. Okay, that will serve the purpose. And I'm just going to line up everything a little bit to the left. Okay, this is all in base 10. I hope nobody thinks this will be challenging. Yes? Yep.
I'm looking at your formula there. It says qi is equal to r x0 y1.
Oh, y0. You're right. I mistyped. Yes, they should be I. Yep, you're right. So they should be I's. Okay, there we go. Thank you. All right. So we'll do this subtraction here. So just like with addition, I will separate the partial difference from the borrow. 0 minus 9 is 1 with a borrow of 1. Is that okay? Does that remind you of the addition thing? It should. And then this is usually just assumed to be a 0. Okay? So 1 minus 0 is a 0. Oh, it's a 1. There we go. So now we have 1 minus 1, which is 0. 0 minus 1 is, this is base 10. 0 minus 1 is, I have no money in my pocket. The bully wants 1, so I have to borrow 10 from one of you. It's 9. So it's a 9 with a borrow of 1. Is that okay? 9 minus 1 is 8. 8 minus 1 is 7. Okay, so let me just double check my math here. Does that work? Yeah, looks like it. Okay. So now, using this as an example in base 10, let's go back and try to figure out how the t's should be expressed. Okay. In other words, we want to look at each case when the t is a 1, and we ask, how did that become a 1? This borrow of a 1 is coming from what? X minus y, right? Okay, so we just write here, we say t subscript I plus 1 can be because of the borrow of xi, yi. Does that make sense? Because b of xi, yi is when we subtract yi from xi, do we end up with a borrow? That's what it's indicating. Okay? And using the base 10 example, yeah, sure. I mean, that's one way to have a borrow of 1. What is the other one? This 0 minus this 1, right? It's qi ti. Very good. So because it can come from one or the other, we'll just use an arithmetic addition for now. So it's the borrow of qi and ti. It is subtracting ti from qi, being there's a possibility that we end up with a borrow. Does that look familiar to you? It should look awfully familiar, right? Okay. So once again, we want to ask the question of, well, how do we express all of this in base 2? So can I erase the base 10 example? Okay, so the base 10 example is only here to remind you that there are 2 ways to end up with a borrow of 1. It can be y subtracted from x, but it can also be t subtracted from q. That's the only purpose of this example. So now we want to say in base 2, we can now express q of I as, oh, we know what to do, right? We just say this is xi not yi, or not xi yi. Okay, same as addition, no difference here. T of I is the borrow of xi, subtracting yi from xi. So we have to remember that this becomes the negation of xi and yi. That is the borrow of this part here. And then we use a plus with a question mark here, which means, can we use or does it have to be arithmetic addition? So I'm leaving it a question at this point. Yep.
Shouldn't it be ti plus 1?
Ti plus 1, you're correct. Yep, this is ti plus 1 for the next column. Thank you. So now the question is, what about the other part? Well, the other part, if you just expand it, it is the negation of qi ti. Just like before. So now the question is, can we have both sides being 1s? Can we have this side and this side being 1 at the same time? Well, let's go ahead and expand q of I, because we know what q of I is supposed to be. So this q of I is the negation of, it's actually a little bit more complex than that. So this q of I is the result of xi minus yi. So when you expand the whole thing, it becomes the negation of xi yi, or, okay, xi and then the negation of yi. Like that. In other words, all I did is to expand q of I into this term, which is which we already had just one row earlier. So now the question is it possible for this side to be true and also for this side to be true at the same time? What do you think? Okay, so I know we are running out of time, but this will only take like 15 seconds. How do you make this term true? Xi has to be a 0 and yi has to be a 1, right?
Yeah.
When that happens, what happens to Q of I? Xi is 0, yi is a 1, I has to be a 1. But remember, Qi is negated first, so it's guaranteed a false. So that means you cannot make both sides being true at the same time. If you cannot make both sides being true at the same time, then we know that we can use an OR in place of an addition. Is that okay? Does that resemble something that you learned in a previous class? Yes? Okay. So next class on next Tuesday, we'll look at subtraction. And just like with addition, we'll look at an approach that is borrow ripple. Okay, instead of carry ripple, it's borrow ripple. And then we'll look into borrow look ahead. Okay? And some of you may think, oh, we have to redo all that math, and then the result is going to be very different. You'll be surprised. It's like, oh, subtraction and addition, really? That's the only difference? So that's what we'll do next Tuesday, and we'll have a lab today for the first part of the 3x3 adder.